For instance, let's say we want to model the population, P, of a beetle on some remote island. So first thing in mathematics, we have to think a moment and what measures change. Hopefully you've already come up with the idea of the derivative. So the change in the population with respect to time. So if P is the population of beetles, then dP dt is the change in population with respect to time, where the little t is time. So what might that be? Well, one possibility would be dP dt is equal to 10. So if t is in months, that means the population of beetles will grow by 10 beetles every month, whether there are 500 beetles on that island, or 10,000 beetles on that island, or 50,000 beetles on that island. The growth would be 10. Now, if you start to think about it, you realize that's probably not going to reflect real life. So then we think, well, what would another model might look like? Well, another model would be dP dt is equal to 1 over 100 times P. Notice the change in population changes based on what the population is. So if P is equal to 500, the change in population with respect to T would be 5. If P is equal to 1,000, it would be 10. If dP is equal to 10,000, it would be 100. This is referred to as a Malthusian model for population. And we find it works sometimes, but usually only for a limited amount of time. You know, it may work for a couple months or a couple years, and then the population tends to veer off from what would be predicted by this model. So that's something, as we go along, we may come back to and try to fix. Some other examples. Radioactive decay. The change in the amount of radioactive isotope is, with respect to time, is equal to a constant K times the amount of that radioactive isotope. Or Newton's law of cooling. The change in temperature with respect to time is equal to a constant times the temperature of the object minus the temperature surrounding the object. Let's look at a little more complicated example. So we're going to think about mixtures, kind of salt dissolved in water. Okay, as we go through this example, what's in red would be kind of given to you, and then what's in black is the things that you would have to figure out. So let's say we have a large tank that contains 300 gallons of salt water. Salt water is flowing into the tank and is being drained off the tank at the same time. However, the salt water coming into the tank doesn't contain the same amount of salt per gallon as the salt that's already in the tank. So we're going to be interested in the amount of salt in the tank at any given time. We're going to let that be A. Then the change in A with respect to time, we have to think about the salt that's coming in the water that's flowing into the tank, but then also the salt that's in the water that's flowing out of the tank. So we'll do the input rate minus the output rate. So let's say we know a little bit more information. So let's say we know that the salt water or brine that flows into the tank contains 2 pounds of salt per gallon and comes in at the rate of 3 gallons per minute. Then the input rate for the salt is going to be given by 2 pounds per gallon times 3 gallons per minute, which is 6 pounds per minute. That's how much salt's coming into the tank at any given moment. I know I'm a mathematician and we don't always pay attention to the units, but paying attention to the units can help you make sure you get the details set up correctly. Suppose the salt water in the tank is kept well mixed and flows out at the rate of 3 gallons per minute. So we have that additional information. Well, we need to figure out what's called the concentration. How much salt is in the water that's flowing out? The problem is it's constantly changing. So we have to ponder a moment and realize, well, at any given moment, we have 8 pounds of salt in the tank, but the water coming in is coming in at the rate of 3 gallons per minute. It's flowing out at the rate of 3 gallons per minute. So that means we keep a constant 300 gallons in this tank. So the concentration is A over 300, and it flows out at the rate of 3 gallons per minute. So we get A over 300 in terms of pounds per gallon times 3 gallons per minute. That gives us A divided by 100, and that's measured in pounds per minute. Then, so pulling all this together, we have the rate of salt coming into the tank, which is 6 minus the rate of the salt going out of the tank, which is A over 100. Notice I'm a mathematician, not a physicist, so I'm dropping the units so I can concentrate on the equation, but the units would be pounds per minute.